Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video explains the role of explained variation in linear correlation. Let's get started. So if we take that linear correlation coefficient R that we've seen in the previous mini lectures and we square it, then we get what's called explained variation, which is the proportion of the variation of y explained by the linear relationship between x and y. So in the previous example we were looking at for the shoe length and the height, we found that there was a linear correlation coefficient value of 0.847. We saw that in the previous mini lecture. So if we square that value, then we get 0.717. This is the value for r squared. And you don't have to put that in your calculator to get it. You can get it straight out of StatCrunch. So if you go back to your results window in StatCrunch and look up at the top, right there underneath where you found the r is r squared, 0.717. So you don't have to put this in your calculator, just get it off the display. What this means is that 71.7% of the variation in the height can be explained by the linear relationship between the lengths of shoe prints and lengths. So essentially what we're looking at, this is a graph that explains a general concept. So we have a regression line where we're making a prediction with our model. Here's where the actual data point lies. And then if we take all the y values for our data points and average them out, we're going to get a mean value. And let's say the mean value is right here. So the difference between the mean value and the model where we're predicting, we can explain that variation because we know where the mean value comes from and we know where the model comes from. The difference between the model and the actual data points, so where we're predicting and where it actually is, we can't explain that. That's unexplained because we know where the model comes from, but we don't know why the data points are where they are. So that's unexplained. And of course, the total of those two, explained and unexplained, is just total deviation or total variation. So when you're looking for explained variation, the way to get the number is just take your r value and square it. Or you can read it off your output here, as you see there in StatCrunch. Sometimes this is also called coefficient of determination. So keep that in mind too as we go along. Here's some examples for us to look at. Let's test our knowledge of what we just learned about explained variation. So for this example, we're asked to determine whether a linear correlation exists and what percent of the variation of y is explained by the linear relationship. So our first example has a sample size of 12, testing at the 5% significance level, and our r value 0.654. So in this example, yes, we're actually going to clear the bar because if we look at where we're at, sample size of 12, so here in our table we take the sample size of 12, so there's our row, and then the column we want is the significance level of 5%, so where those two match up, 0.576 gives us our critical value. The value we get for r is greater than that, so therefore we've cleared the bar. Yes, there is a linear relationship. And then to get the second part, we just take that value and square it, and that gives us the percent variation. So that's all there is to it. Why don't you try the next one on your own? So sample size of 30 at the 1% significance level with an r value of 0.453. Good, pause the video, come back, we'll see how well you did. Okay, let's check out how well you did here. So we've got a linear relationship here? No, we don't have a linear relationship because we're not high enough to clear the bar. So here's our threshold value, 0.463, based on this sample size and significance level. And you can see that here in the table. And then we don't have enough r to get over that threshold, so we did not clear the bar. And because we didn't clear the bar, no percent of the variation is explained by the linear relationship because there is no linear relationship. Try the next one. Stop the video, test this out, come back, see how well you did. Okay, so here you should find that there is a linear relationship. So we do have linear correlation, and we do clear the bar, and when you square that R value, you get the percent variation that's explained, so the explained variation. Here's another one. Try this one on for size. Pause the video, test this out, see how you do, come back. Okay, so here you should find that yes, there is linear correlation, and the percent explained variation is going to be 0.805, so 80.5%. Here's another example. Go ahead and pause the video once more, test this out, come back, we'll see how you did. Here we don't have linear correlation because look, our critical R value, 0.396, we land smack dab straight into it. We're not clearing the bar, we're running smack dab into it. So no, there is no linear correlation, and the percent variation that's explained is nothing because there is no linear relationship. Let's look at one more before we go on. So sample size of 2, 1% significance level, R value of 1. Well, here there is no critical R value. So if you just take two lines and put them on a graph, you're going to draw a straight line. That line of best fit is going to go through both your points. So yes, you do have linear correlation. It's perfect linear correlation, but that's what you get when you've only got 2 points to draw your line through. And then, of course, you take one and you square it, you find 100% of your variation in Y is explained by the linear relationship. Let's take a look now at serial killers, because everyone knows that sugar kills. So we're going to make you feel guilty for eating Cocoa Puffs and Cinnamon Toast Crunch in the morning. So here we got a linear correlation coefficient of 0.149. Here's the linear regression equation that comes out of that data. There's 16 different cereals we're comparing. So if you take the average amount of sugar is 0.295 grams, average amount of calories 3.76. And yeah, I don't know where that number's coming from, but that's just what the problem said. So what's the value of the coefficient of determination, and what percent of the total variation in the number of calories can be explained by the linear correlation? Well, the coefficient of determination is just another way of saying explained variation. So here we're just going to square our R value. So we just take that R value and square it. The explained variation is again going to be the same thing, but we're going to express this in percent form. So we just take that decimal point, move it over 2 places to the right. 2.22% is our explained variation. Some common errors that you run into. First of all, some students wrongly conclude that, if there's a relationship between two variables, it means that one causes the other. Just because there's a relationship doesn't mean that it's cause and effect. So it could be something else, and you don't really know that until you dig into the data to find out more about what's going on. Correlation never implies causality. Okay? All it means is that there's a relationship there. It doesn't mean it's one of, it could be cause and effect, but it doesn't mean that it has to be that. Another mistake some students make is with averages. Students nowadays tend not to make this mistake because, all your calculations done by computers. So you tend not to make this mistake. But back in the old days, we were using, some students would use averages instead of individual values to simplify that monstrosity of a calculation for R. Yeah, it doesn't work too well because it suppresses the individual variation you get in your data points. So it's not a good idea to use averages. But again, that's not going to be a problem for most students nowadays. And then some students give up looking for a relationship if a linear one doesn't exist. And as I've said before, there are many real-world relationships that are nonlinear. So if you don't find a linear relationship, just look somewhere else. Again, correlation does not imply causality. And that brings us to the end of this mini lecture. I hope you found it helpful, and I'll see you in the next video.